All right. Good morning. Welcome back. Hope everybody's doing okay. Can you guys hear me?
Yeah, we can.
Okay, cool. All right. So we basically only have 3 more lectures left this semester. And so what I'm going to do, basically what I'll need to do is finish off chapters 33 and 34. Next Monday's lecture will basically be on chapter 34. This week, I'm hoping to get through chapter 33. I should be able to. Okay. So my goals for today are to talk about this concept called phasors, inductors in AC circuits, capacitors in AC circuits, RL circuits, and RLC circuits. So I have quite a bit to get through. The chapter 32 homework's due tonight. Make sure you work on your motor lab. I'm concerned a lot of people have to show up today during the lab to do the transient lab. And I will introduce, most likely today, the last lab. And then I'm going to talk some more about the last lab, or at least the last lab where you collect data, on Friday. Okay? So I will introduce parts of the lab today. Basically, I'm going to tell you what you need to do, at least for the procedure. The procedure is pretty easy. Okay? And then on Friday, I'll tell you a little bit about how to do the calculations, and I'll do some more theory regarding RLC circuits. Okay? So let me begin by talking about, I'm going to introduce this new concept called phasors. It's a mathematical concept, and it only works for circuits that are driven by a sinusoidal power supply. This whole chapter is on AC circuits, and in particular, the case where they're driven by a sinusoidal power supply. This concept called a phasor is going to be very useful in helping us analyze circuits. It won't allow us to analyze the most complex circuits, but it will allow us to analyze some of the basic ones. Okay? So let me just say what a phasor is. This has nothing to do with Star Trek. Okay? A phasor is used to represent either a voltage or a current, generally, in this case. Okay? But it's a vector that's placed in a standard XY coordinate system. Okay. This vector can represent any physical quantity that varies sinusoidally with time. So, for example, this guy or this guy. Okay, in our case, it's going to be that. When I teach 215, I use the same idea to describe the time-dependent electric field that depend sinusoidally with time. Okay, and I use it as a mathematical tool to help us more easily analyze systems. And that's what we're going to be doing here. Okay, the concept of the phasors is going to allow us to study circuits with resistors, capacitors, and inductors in series without really having me to solve a differential equation. Okay? Uh-oh. It's used to, again, it's really used to represent any physical property that changes periodically, sinusoidally, in fact. The length of the vector represents the maximum value of the properties, either V sub m or I sub m. This vector rotates in time at the frequency given in the expression. So for something coming out of the standard outlet, 60 hertz, imagine this thing rotates, does 60 cycles in 1 second. And we're just going to look at it, a snapshot of it at some particular instant in time. This angle is omega times time. It rotates counterclockwise with the same frequency as a signal. Okay? The instantaneous value of the physical quantity is the projection of this vector onto the x-axis. So let me say something about this. Our book does not do that. Our book projects it onto the y-axis. Everybody else projects this onto the x-axis, okay? Except for our book. And the reason why it's important to project onto the x-axis is when you take a more advanced course in circuit analysis, this graph is going to be this graph is really in a complex plane. The horizontal axis are real numbers. The vertical axis are complex numbers. Okay? And so generally the cosine term or the x-axis term is the real part of the complex number. When you take, those of you who take Engineering 17 are going to treat these quantities as complex numbers. They're called phasors, but you're not going to be plotting them. You're going to be just writing them as complex numbers. Now we can display as many phasors on this plot as I need. By adding phasors, I can add voltages. It's like adding vectors. And the result of drawing a bunch of phasors together is called a Phasor diagram. These diagrams are used to help us to look at AC circuits. And like I said, in 215, they're also going to be used to look at electric fields that vary sinusoidally with time. Okay? Phasors are not physical quantities. They're just mathematical constructs that better helps us to better understand AC circuits. So that way we can avoid solving second-order differential equations when we analyze, for example, the RLC circuit. So let me show you a figure of a phasor for the circuit we looked at the other day. They just had a resistor. This is a phasor diagram of a circuit that just had a resistor in it. The voltage and the current were in phase, and so I show you the voltage and current plot as a function of time, and then to the right of that is the phasor diagram at some instant in time so that the angle is omega times t. The red, or the magenta, represents V, the voltage, and the blue represents the current. The projection onto the x-axis represents the value of V or I at any instant in time. Now, in this particular case, V and I are in phase, but when we look at voltages, when we look at circuits that have inductors and capacitors and resistors in them, V and I are not going to be in phase. And we'll see that soon. I'm going to use this idea of the phasor to analyze various circuits. So let's start with an inductor. Let's put an inductor in a circuit, power supply and inductor. And really, the phasor diagram is not going to be that useful for just having a power supply connected to an inductor. It's going to be useful when you have power supply, inductor, and resistor in series. Well, let's look at this case because we need to understand the behavior of the inductor in an AC circuit. Okay. So we're given that the power supply voltage is V sub m cosine omega t. And the voltage across the inductor is L di over dt. But that's got to be equal to the power supply voltage. So how do I get I? How do I get I from here? What would you do? Then what do? You integrate, right? So the current in the circuit, in this particular circuit, is the power supply voltage divided by omega times the inductance times sine of omega t. And you right away see that the voltage and the current are not in phase. They're 90 degrees out of phase. Okay? And in fact, we can write this in the following way. You get the same result. And we see then that the current is behind the voltage by 90 degrees, pi over 2. Okay. Furthermore, we can define x sub L equals omega times L, so that we can write I equals V sub m over x sub L cosine omega t minus pi over 2. We're going to call x sub L the inductive reactance. Any questions so far? And I'm going to denote this angle as phi. So I'm going to write the current. In general, what I'm going to do is write the current like this. Or I'll write it this way. Where this angle phi is measured with respect to the power supply voltage. So in this particular case, the current lags the voltage by 90 degrees. Okay? We can also write the voltage across the inductor in the following way. Any questions? You may be wondering how he got from here to here. Okay. But this is just the power. This is basically the power supply voltage, the maximum power supply voltage. No questions?
I was wondering. Thank you.
You were wondering that?
I was wondering. I'm just kind of in the mode of just accepting the things that are told to me. Though I feel limited in my capacity to figure things out right now.
So what if we expanded that? And how do I? What is this angle pi over 2? What that represent? I mean, so if I plotted my voltage in a phasor diagram, if I plotted V sub L, the current would look like this. And my phase angle is 90 degrees. How can I rate, how can I, well, I mean, if this is 90 degrees, cosine of pi over 2 is 0. Sine of pi over 2 equals 1. I can write this as V sub L over V of the power supply. Isn't that true? I mean, isn't V sub L over the V of the power supply equal to 1?
When current is maximized across the conductor, or I'm sorry, across the inductor.
Well, I mean, these are the maximum values. I have it set up so that the phasors always, this guy always represents the maximum value.
Okay.
I mean, this thing rotates. This whole thing rotates in time counterclockwise. These two, just imagine I have two sticks at 90 degrees from each other.
Yeah.
And they just thing keeps rotating really fast. Okay. Their relative orientation stays the same. But then, how do I write down phi? Well, it's got to be the power supply the voltage across the inductor divided by the power supply voltage. And what if I expanded this? Because you were concerned about how I got from here to here. a second. Oh, yeah. Did I do that okay? Seems like. I did something strange there. Oh, cosine, cosine, sine, sine, right?
Yep, I just dug out my identities. That's right.
Okay, that's better. Okay, so then this term is gone. Then what? This is what sine of pi over 2 is, right?
Yeah.
And v sub s is also the same thing as v sub m, sorry. I did something strange, sorry.
Did you leave that sign there on purpose when you erased the pi over 2?
Oh, yeah, yeah. Yeah, but I was trying to go back to cosine. I was trying to go back to that.
Yeah.
I did something strange. I was trying to convince you, but I got to redo it. I'm sorry.
Okay.
I'm gonna have to redo that.
It's all right.
Yeah. But this has to be v sub m. I'll have to do that again. Sorry. I don't want to spend too much time on that, but
Yeah, we can move on.
anyway, this has to be v sub m, and this has to work out to cosine omega t. I think when I do the RL circuit, it'll become apparent why it changes. I was trying to do it before I introduced phi a little bit more formally, okay, which I've never done before, but I wanted to see if I can get it done. Do it. Sorry about that. Let me show you a picture of the phasor diagram. And I drew it at an arbitrary angle. And I will tell you, when you draw the phasor diagrams, drawing it like you see in the figure is actually a little bit inconvenient if you're trying to analyze a circuit. Okay? Let me do a circuit that has a resistor in it. So this is just a circuit with a inductor. The inductor is ideal. The current always lags the voltage by 90 degrees. That's always the case. Okay? And again, the X sub L is called the inductive reactance. And the inductive reactance represents a measure of the opposition to a changing current in an AC circuit. Now, there's a good question you see on the slide. X sub L increases with omega. Why? Why does X sub L increase with omega? Where does X sub L come from? It comes from a time-varying magnetic field. The faster this thing changes, the faster the field changes, the bigger d phi dt is. And so you have a greater opposition to a changing current. So let's do a case where we throw in a resistor. Now, if I throw in a resistor, I got to use Kirchhoff's laws and solve a second-order differential equation. I don't want to do that. This is where the power of the Phasor diagram comes in. I've looked at a circuit containing a resistor by itself, and I've looked at a circuit containing an inductor by itself. We know that the voltage across the inductor is ahead of the current through the inductor by 90 degrees. I know that the current and the voltage through the resistor and the voltage across the resistor are in phase. We showed that. So this is what I'm going to do. I'm going to draw a Phasor diagram for the system. They're in series, so they're both going to have the same current through them, right? So what I'm going to do is I'm going to draw a phasor representing my total current. And I know the voltage across the resistor is in phase. In other words, it's going to be parallel to this current. It's going to be a different size vector. So I'm going to draw the voltage across the resistor. I also know that the voltage across the inductor is ahead by 90 degrees, and I'm running out of colors. Let me know if you can see green, if it's too faint. Can you guys see that okay?
It's hard to tell the color apart, but we can see it.
You can see it? Okay. I'm trying to make them different colors, but... And so that's V sub L, that's V sub R. And the sum of those two voltages have to be equal to what? They have to be equal to the power supply voltage. So I'm going to use the parallelogram method here, and I'm going to add the two vectors. This is the power supply voltage. You can call it V sub M or V sub S. It's called either one. This is the phase angle between the power supply voltage and the current through the resistor. It's also the phase angle between the power supply voltage and the voltage through the resistor. When I draw my Phasor diagram, I always draw this with I horizontal. I don't care what omega times time is. It just makes it more convenient for me to draw the picture. Okay? Because if I choose an arbitrary omega times time, then this thing is going to be rotated some weird angle. So I always put this guy horizontal. It makes life a lot easier for me. Omega times time could be whatever. That way I can clearly see the angle between the power supply voltage and the current through the resistor. So I'm just adding vectors when I draw Phasor diagrams. And so the voltage, the power supply voltage, is going to be V sub R squared plus V sub L squared. You cannot say that if this is 30 volts and this is 40 volts, you cannot say that this is 70 volts. If this is 30 volts and that's 40 volts, this will be 50 volts. Because you're adding trig functions, you're adding vectors, you're adding phasors. You're not adding them numerically anymore. This is not a DC circuit. Does that make sense? You're adding two quantities that are out of phase. These two voltages are going to be 90 degrees out of phase with each other. So you can't just take 30 plus 40. You're adding trig functions. Does that make sense?
Yeah, and like you said, the V and the L, the VL and the VR are their maximum values, so the magnitude of those vectors never changes.
Yeah, and what we do when we look at these circuits, we only focus on the magnitudes. When we look at the AC circuits and we analyze them, we really focus on their magnitudes. Or the RMS values, which is basically going to be these values divided by the square root of 2. Okay? When you do your lab, you're going to be measuring the RMS value because that's what the multimeter measures. But whether you're measuring the maximum voltages, whether you're analyzing the maximum voltages or the RMS value, the angles are not going to change. It's just going to rescale these vectors. Okay? Well, they're both going to have the same current through them, so I can write this in the following way. And I can factor out the I from this thing. And so I max, is your power supply voltage. And this is the maximum value, right? These are all maximum value. And this term down here is called the impedance. We could denote it with the letter Z. Normally I introduce this later, but it's the R squared plus whatever the other term is. When we add the capacitor in the circuit, I'm going to add another term into here. So this is the impedance. So I sub m is the power supply voltage over Z. And of course, if we were doing RMS values, then I would divide this by the square root of 2, right? IRMS is VRMS over Z. Right, because both of these terms have to be divided by the square root of 2. How do I get that angle? Well, I just use trig. I use opposite over adjacent. Tangent of phi is V sub L over V sub I, but then they both have a current in common. So tangent of phi is just X sub L over R. I have everything summarized in this figure. Let me blow up the figure. Everything about that circuit is summarized here. Oops, I missed the chat, sorry. Yeah, you can't, Matthew, you can solve a second order inhomogeneous equation. In fact, I'm going to do that on Friday. I'm going to use the method of guessing again. Yeah, and you can do it if you don't know a sign, what the shape of the wave is. Square wave is a little more complicated because you have to write you have to write the square wave as a series of sine and cosines. And so that's a little bit more complicated. But sinusoidal phones, you can easily do those. And so I'll do it on Friday, but I'm going to use the method of guessing. Okay, so everything is summarized in that figure. I have sine of phi in there, and I have cosine of phi. This is what I was trying to do earlier with that equation. Because R was 0 in the previous circuit. So Sean, you see the last line that has V sub s equals V sub m with all those trig terms?
Yeah.
Yeah, I was trying to do that before introducing this circuit, and that was a mistake on my part. But if you use that equation that you see there, where phi is pi over 2, you get the cosine term come out of it.
Okay.
Okay? And I apologize, I should have done that. Okay? I should have actually waited to this point, and then you would see where that comes from. But I got a little bit ahead of myself. I kind of went off on a tangent. Okay. So what else can we learn from this circuit? Hold on, I had trouble with my mouse. We can write the voltage across the inductor and the voltage across the resistor as shown in the figure. And again, we're more interested in the maximum values. So let me write just the maximum values down. V sub L is I sub m, x sub L. I sub m is this. And let me put the omegas in. And let me write V sub R too. Now, what happens when the frequency gets bigger and bigger? What happens when the frequency gets bigger and bigger? What happens to this term?
Goes to 0. Assuming infinitely large, it goes to 0.
Not this one, right? This one does.
Oh, yeah, because it's up there on top as well.
Yeah, this goes to 1. This goes to V sub s. This term, omega L over the square root of R squared plus omega L squared, this actually goes to V sub s. And this goes to 0. So all the voltage ends up being across the inductor. When omega goes to 0, this goes to 0, and this is a maximum. So if you have a circuit, I'm going to redraw my circuit. I'm going to draw it like this, and I hook up some load across the inductor. At high frequencies, what's going to happen? All the voltage is going to be on this thing. And we say that when you hook up your circuit this way, so your load's across the inductor, this is called a high-pass filter. Because it allows high frequencies through. If I switch these two in the circuit, R is the voltage across the resistor is maximized when omega is small. Then you have something called a low-pass filter. You'll see the term high-pass filter and low-pass filter in the textbook as you're reading it and in the homework. We're not going to get into the details of the high-pass and low-pass filters, but they're discussed in the book. Okay, when you take Engineering 17, you'll learn more about them. Typically in an engineering courses, they look at the ratio of V sub L over V sub S. And I think they call it a transfer function, if I remember correctly, which is basically the ratio of X sub L over the total impedance. And they look at how that behaves as a function of frequency. Okay, so for example, and they make, engineers will make a plot of this as a function of frequency and look at the behavior. And they'll do it for more complicated circuits than this. Okay, but this is an important circuit in engineering and in circuit design. Although usually one uses capacitors and resistors for high pass and low pass filters because inductors have inherent issues with them as opposed to capacitors. Okay, so that's an example where I used a phasor diagram to study a circuit. So let's take a look at now a capacitor. Just a capacitor and a power supply. I won't use the phasor diagram for this one because the capacitor is all by itself. And I'm not going to do a circuit with a capacitor and a resistor, and just in the interest of time, but you should be able to do that one. Just doing a simple phasor diagram. Okay, so here we have a capacitor. The power supply voltage, and I should be consistent. I should call this V sub M all the time, but I use V sub M and V sub S interchangeably. Okay, I use these interchangeably. The book does too. So the voltage across this thing has to be and then Q is C times V sub C but what about I? What's I? I got to take the derivative. So the current through the capacitor is going to be dq dt now, if you remember, when we just looked at the inductor, we said when we looked at the resistor only, notice I have some sort of voltage divided by some quantity. I'm trying to make them look like Ohm's law. So in keeping with that, I'm going to define X sub c as 1 over omega c. So then I can say I sub c Now in this case, the current is ahead of the voltage by 90 degrees. The current is ahead of the voltage by 90 degrees. The current leads the voltage when you have a capacitor in a circuit. Now granted, I've drawn just a capacitor by itself, but the current through the capacitor, if I can say that, leads the voltage by pi over 2, 90 degrees. And so in general, we can say I sub c is V sub m over X sub c cosine of omega t plus phi. That's a c. Okay. So phi equals 0 for resistors, phi equals minus pi over 2 for capacitors, and phi equals plus pi over 2 for inductors. Sorry. So if I were to draw the phasor diagram, let me make this picture bigger for everybody to see. And when I make these drawings on the PowerPoints, I make them at arbitrary angles, but that's what it looks like. The current's ahead of the voltage by 90 degrees. Now you should be able to do the RC circuit. Questions? Okay. So our goal really in this chapter is really to look at what happens when we combine the R, the L, and the C, and that's going to be your lab. What happens when we combine them? Now, one thing I forgot to do, I want to show you an example of the RL circuit before I go on. So let me show you an example of the RL circuit with an AC power supply. Can you folks see that okay?
Yeah.
Okay. So I have the resistor here, the inductor here. Basically some same components as you're using in the transient circuit. I'm just using a different voltage, it's sinusoidal. Okay? And I'm looking at the voltage across the resistor. And I'm going to make the frequency really low. I'm going to go down to 100 hertz. Now, what is the phase angle? The phase angle is the difference in angle between the peaks of the power supply voltage, which is this one, and the voltage across the resistor, which is a smaller one. Are they pretty much in phase?
They look like it.
They pretty much look at it. So tangent of phi was equal to omega times L over R when we analyze the circuit. And as omega goes to infinity, this angle is going to go to 90 degrees. Now, watch what happens when I increase the frequency. Do you see the phase shift increasing? The angle between the peaks? Look at how far apart the peaks are now. You guys see that?
Yes.
So the peaks, the peaks shift. There's a phase shift in the peaks as I change the frequency. And that's one of the things. So when you do the lab, the RLC lab, you need to notice that. What happens to the peaks at different frequencies? You got to notice it. Normally when we do this lab, in the past, we would actually have you measure them, but I'm not having you do that this semester. I just want you to make an observation. What happens to the peaks as you change the frequency? Do they shift? What, whatever. When are they at the same? When are the peaks? When do the peaks match up? Okay. So when you do the RLC lab, you're going to be looking at the voltage across the inductor, the voltage across the capacitor, the current through the circuit, and you're going to be also analyzing, you're going to be viewing the phase shift. You're going to have 5 instruments making measurements at the same time in your circuit. And this instrument will be making 2 measurements itself. Okay. So you should be able to make the drawing for the RC circuit, the Phasor diagram. Now, I defined this term. This is called the capacitive reactance. So X sub L was the inductive reactance. X sub C is called the capacitive reactance. And if you look at the units for this, the unit is ohms. If you look at the units for this, the unit is ohms. Right, because this is an ohm second. An ohm second divided by a second gives you ohms. So these have units of ohms, and of course R has units of ohms. Okay. So we're writing everything so it looks like Ohm's law, but really not exactly. Okay. All right. So one of the things about the inductive reactance, the capacitive reactance, as this goes to infinity, as omega goes to infinity, this goes to 0. As omega goes to 0, this goes to this ratio goes to infinity. And that should make sense because when you have a DC circuit, once the capacitor is charged, what happens?
Current through it stops.
Yeah. Okay? But when omega goes to infinity, the capacitor never has a charge, doesn't have a chance to charge up at all. It acts like a wire. So as omega goes to infinity, the capacitor acts like a wire. As omega goes to 0, the capacitor acts like an open circuit. But of course, as omega goes to 0, let's see, as omega goes to infinity, what happens here?
As in which equation?
Here. As omega goes to infinity, does your current blow up? Well, yeah, it's as if you have no resistance in your circuit. Okay? Of course, we're talking about the ideal case. All circuits have some sort of resistance in them. All right, so what we want to look at now is the case where we have the resistor, the capacitor, and inductor in series. And solving this would give you a second order, an inhomogeneous second order differential equation with constant coefficients. That's the technical term. And I will try to solve that on Friday in lab. Okay? We'll see how much time we have. All right, so I'm going to put all three components into a circuit. And I don't want to solve the differential equation. So what I'm going to do is I'm going to draw my Phasor diagram. And unfortunately, I don't have enough colors to draw my figure. Okay. I know that the current through each one of these elements is going to be the same. All right, it's a series circuit. That has to be true. We got to conserve charge. The voltages across each element will have the same phase relationship to the current as the isolated elements. That has to be true too. And I'm going to assume that the power supply voltage, V sub S, the instantaneous value is V sub M cosine omega t. And again, I'm really going to focus on the maximum values. Okay, I'm going to really focus on the maximum values. The time-dependent part, one can write down, but we usually don't play. We just don't play around with the time-dependent parts. We can write I is I sub m cosine omega t minus phi and figure out what phi is. So we can write I as a function of time explicitly, but we're more interested in this. Or the RMS value. So I'm going to proceed the same way I did before. I'm going to say, okay, well, I'm just going to draw my diagram with the current along the x-axis. They're all going to have the same current. So I'm going to draw a picture. Like that. Then I'm going to draw the voltage across the resistor. What did we say about the inductor? The voltage across the inductor leads the current by 90 degrees. So let me draw that in. Yeah, I'm going to use green again, sorry. What about the capacitor? What do we do with the capacitor? What do we say about the capacitor? We said that the voltage across the capacitor is behind the current, right? The voltage across the capacitor is behind the current through it by 90 degrees. Let me know if you can see this, okay? Can you see that or not?
So that's pretty faint.
It's really faint. Okay, I'm going to draw it in black. I don't have enough colors. We ran out of colors. That you can see, right?
Barely.
Yes.
Okay. So that's my Phasor diagram for the three voltages. And really what I'm doing is adding vectors. These two are 180 degrees out of phase. So the difference between these two, let me draw this up here. Then I used the parallelogram method. Sorry, I have to do this. There's your power supply voltage. That's your phase angle. So I have this triangle here, this right triangle, which I call the impedance triangle. And I can write my voltage across the power supply in the following way. But I know that they all have the same current through them. And I can factor out the I. Okay, so then I max is the power supply voltage maximum over this is called the total reactance for the circuit, and then this is just the resistance. The whole denominator is called the impedance. Then I can explicitly put in values for X sub L and X sub C. Pretty much know everything about my circuit now. Okay, I pretty much know everything about my circuit. And then I've drawn two Phasor diagrams One of them is the one I used to analyze the circuit, the one on the left. And then the one on the right, I drew it at some arbitrary angle. I just rotated the whole darn thing because I think that whole thing rotates with time. I did it some time omega times, some angle omega times time. Phi is always the angle between the power supply voltage and the voltage across the resistor. So you have everything you need to know in that figure. Okay, that's just reproducing what I drew on the board. And then there's another case where I rotated it through some angle. But the relative angles between all the vectors still remains the same. And then, like I did before, the impedance, as I wrote on the board, is given by that function. And it's really a generalized way of writing Ohm's law. So now the current depends on the value of R, the value of L, the value of C, and omega, which is 2 pi times the frequency. That triangle that I drew, this triangle, there it is. This triangle right here is called the impedance triangle. And that triangle tells me everything I need to know about the RLC circuit. If you memorize that triangle, you'll know everything about it. You'll know everything about the RLC circuit. Okay? For example, tangent of phi is opposite over adjacent. These all have an I in common, and I can factor it out. I can write it like that. Cosine of phi can also be written this way. This impedance triangle I drew with the V's, the one you see in the slide, has X's. If you factor out the I, then you get your impedances and resistances. Sine of phi so everything you need to know is in that triangle you draw. If you memorize that triangle, you can figure out everything else. Oops, sorry, I didn't see that. Questions on this? As you work through the problems, this gets easier for you. I know there's a lot of stuff right now. Now, let's look at the phase angle. Let's look at this angle. When the inductive reactance is bigger than the capacitive reactance, this angle's positive. When the capacitive reactance is bigger than the inductive reactance, the angle's negative because our numerator is negative. So when the inductive reactance is bigger than the capacitive reactance, the current is going to be behind the power supply voltage. However, when the the capacitive reactance is bigger than inductive reactance, then the voltage will be behind the current. Okay. How long these are really depend on the values of L, C, and omega. There is a frequency in which these two are equal, the phase angle is 0, okay? There's an angle in which there's a frequency in which this thing is 0, the phase angle is 0. And so this guy and this guy are in phase when that happens. We call that resonance because you get maximum energy transfer to the resistor. Okay? Basically, when these two are equal, this guy disappears, and your current is the voltage divided by the resistance. That's it. It acts as if you have a purely resistive circuit when you're at resonance. Okay? Can we figure out the frequency in which that happens? When does resonance occur? Well, we just set x of L equal to x of C. So let's do that. Oops. So the frequency in which phi equals 0 is this.
I've seen that before somewhere.
Yeah, when we did the LC circuit, right? We did the oscillating circuit in the previous chapter. That's kind of why we talk about that. We talk about it because that comes up often. And we also saw when I did the RLC, the transient response, you saw that product also. So this is called a resonance frequency, and a lot of times you write F naught, or omega naught equal 1 over the square root of LC. This is where the phase angle is 0, and that's where you get maximum current in your circuit. Okay? And the current just V sub m over R. So, in an LRC circuit, there's really no power losses as a result of a capacitor or as a result of the resistor. Your power loss is due to the resistor. Sorry. So there's no power loss due to the inductor. There's no power loss due to the capacitor. There's only power loss due to the resistor. Now, when I talk about the inductor, I'm assuming an ideal inductor. So what's the power loss in the RLC circuit? So let's just look at the expression for the power loss. Let me rewrite this. Okay. I have that in your slide. I want to look at the average power loss. I want over a cycle. And in order for me to do that, to look at the average power loss, I'm going to expand this thing out. I'm going to expand this guy out. So it's cosine, cosine, sine, sine. Let's see. Oops, this is cosine omega t, sorry. Okay. Let me distribute this through. I want to find the average of this over a cycle. Let's say I integrate from minus pi to pi. That's a cycle, right? Or I can go from 0 to pi over 2. It doesn't matter. If I average this over the cycle, what does this come out to be?
Does the sine omega t, cosine omega t, does that multiply to equal 1?
Well, in other words, I want to find the average. That's going to be the average of that function. Now, this is basically the sine of 2 phi. Right? This is the sine of 2 omega t. What's the average of sine?
Average of sine over a phase is 0?
Yeah, because you get the same positive area here as you have negative area here, right? So this term is 0. It's an odd function. If you integrate an odd function over a symmetric interval, you get 0. What's the average of cosine squared? We already talked about that. The average of cosine squared is a half. That's P average. Cosine of phi is called a power factor. Please remember what that is. Everybody forgets what the power factor is. Cosine of phi is R over Z. Everybody forgets what that means. So when you're in phase, when you're at resonance, this thing is 1. Okay? That's what P average is. So let me see. The power factor can also be written as V sub R over V sub N. So let me do that. These cancel. And so what does that leave me? But V sub R is I sub M times R. But I sub M is the square root of 2 IRMS. That's the average power loss in a cycle. I squared RMS times R. So you can write it either this way or in terms of the phase, the power factor. Remember what the power factor is. Please don't forget what the power factor is. I'll put a question involving the power factor in an exam. Students come up to me and say, what's the power factor? So don't forget what that is. So where does the energy go? Well, it goes to the resistor. The resistor uses up all that energy. So the average power delivered by the generator is dissipated as heat in the resistor. Okay, I think what I'm going to do, I'm going to stop here. It's already 10:56. Okay, I don't want to go too far. And so on Wednesday, I'm going to finish off the chapter. I'm going to say a little bit more about this. I'm going to talk about the experiment that you're going to be doing. So in the experiment, this is what you'll be measuring. I guess I'll say something about the experiment. You'll have a resistor. You'll have a capacitor, an inductor, and you're going to be measuring current. You're going to be measuring the voltage across the capacitor, and you're going to be measuring the voltage across the inductors. You're going to be measuring this, you're going to be measuring this, you're going to be measuring this. You're also going to be monitoring the RMS voltage. You're also going to have this in the scope. Actually, this should be at the end of the circuit. And you'll also have this connected to the scope. So we'll have 1, 2, 3, 4, 5, 6 things being measured simultaneously. Okay, but the scope, the scope you're going to just be observing. You're going to be measuring this, this, and you'll be monitoring the RMS voltage as you're changing the frequency, because sometimes it changes. Okay, that's your circuit. It's essentially the same. So what you want to do is wire the RLC circuit like you did for the transient lab, and then hook the instruments up into the circuit. Always, because otherwise it's going to look too complicated. Any questions? Okay, I guess we'll stop here. Finish off the homework tonight and then start on the next chapter. We'll see you on Wednesday, or if I might see you today if you come to lab.